Suppose that there is a trial with two possible outcomes that are usually called success and failure. These are just, how to say, conventional names. So this success can be something very far from success in our ordinary sense, but still this is just a terminology. That is why these outcomes are usually called a success and a failure. And suppose that this trial is repeated many times and two conditions are met. The first condition is that outcomes of these trials do not depend on each other. So, classical example of such a situation is the flipping of a coin. So you flip a coin, and each time the result of flipping does not depend on the result of other flippings. So if you flip a coin, let's say 10 times, the result of the fifth flipping does not depend on the result of the first one or of the second one, and so on. And the second condition is that probabilities of these outcomes, probability of success and failure, are constant during this series of trials. So probabilities of success and a failure do not change. If these two conditions are fulfilled, we call this a series of Bernoulli trials, or Bernoulli series of trials, or an experiment done according to the Bernoulli scheme. So we use the name of Bernoulli to describe this situation. So, sometimes there are situations very close in their physical sense, but one of them is a series of Bernoulli trials and the other one is not. So let me give an example. For example, you have a box and there are 20 apples inside this box, and 15 of them are good ones and 5 of them are rotten. And the experiment is choosing one apple at random, and if you choose an apple, you look at apple and you see, you understand if it is good or not, and if you put it back to the box, this is a series of Bernoulli trials, as every time a probability to get a good apple is 15 divided by 20. It doesn't change. It is the same. And so probability of each trial does not affect probability of the other anyhow. But if you look at the apple, and for example, if the apple is rotten, if it is not good, you throw it away. So in this case, this is not a series of Bernoulli trials, as outcome of a trial can affect outcome of the next one. So if the first apple is good, in the second trial, you will have the same probabilities for good and rotten apple. And if the first apple is not good, and you throw it away, and so only 19 apples are left, and so probabilities change. The probability to get a good apple is now 15 divided by 19, not by 20, and probability of getting a rotten apple is also 4 divided by 19. So here we see that outcome of a trial affects outcomes of the next trials, and that is why this is not a series of Bernoulli trials, as our conditions are not met here. So suppose that we have a series of Bernoulli trials, and we know number of trials, and we know probability of success for each single trial. And now I want to find probability that number of successes in the whole series will be equal to a given number. This can be done with the Bernoulli's formula. So this is probability that there will be exactly k successes in a series of n Bernoulli trials. And small p is a probability of success in each single trial. So here you see n choose k, so number of combinations, times p to the power of k times 1 minus p to the power of n minus k. So in this formula, the expression is multiplied by the number of combinations, by n choose k, because it doesn't matter which trials are successful ones. So we are interested only in total number of successes, not in particular trials that are successful or not. So, for example, if we want to know what is the probability that there will be exactly 3 heads when we flip a coin 5 times. So if we have heads in the first flipping, in the second one, and in the third one, it is okay for us. If we had heads in the first flipping, the third one, and the fifth one, it's also okay for us. So it doesn't matter what are the numbers of flippings when where we get these heads. It is only total number of heads is important for us. So that is why we multiply this p to the power of k times 1 minus p to the power of n minus k by the number of combinations. And now let's solve an example. There is a marksman that shoots at a target, and he shoots until his third miss. So he's shooting, and 3 misses are acceptable. And the question is, what is the probability that he will make exactly 7 shots? If the probability of hitting a target for each single shot is equal to, let us say, 0.8. So this is the probability to hit a target every time he's shooting. So students usually tell me, so everything is very simple, we just need to apply the Bernoulli formula here. So you say that there are 7 shots, so n is equal to 7. Then you say that there are 3 misses, so k is equal to 3, and probability of a miss is 1 minus 0.8, 0.2. That's all. We just need to substitute these 3 numbers, 7, 3, and 0.2, to the Bernoulli formula. So to this formula, we have just discussed. N choose k, p to the power of k, 1 minus p to the power of n minus k. So n is 7, k is 3, p is 0.2, and that's all. But if we do so, we will find the probability that there will be exactly 3 misses in 7 shots, after 7 shots. And so these 3 misses, their places among these 7 attempts, so are not important if we do so. For example, if we just substitute the numbers as I have just told you, so we'll get the probability of many different outcomes. For example, like miss, 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 and then hit, 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 hit. This is also acceptable if we just apply this formula, and that's all. So, and we are told that he is shooting until his 3rd miss. So that means that shooting ends only when the 3rd miss takes place. So that means that the 7th attempt must be failure. So he must miss when he's shooting the 7th time. And among first 6 attempts, there are to be 2 misses. So actually, probability, the event of interest, our event of interest, is not 3 misses in 7 shootings, but 2 misses in first 6 shootings and missing in the last, the 7th shot. So let event A be 2 misses in first 6 attempts, and event B is that the 7th shot ends up with a miss. And the probability we need to find is probability of A intersection B. And I haven't told you anything about their independence, but let's say that shots are independent, so that result of any shot does not depend on the result of the others. Maybe it is not fully true in our real life, but let's suppose that they are independent. So, if we suppose that they are independent, if we assume their independence, then this is P of A times P of B. For independent events, this is true. And so, P of A can be found with the Bernoulli formula. So, P of A is the probability of 2 successes in 6 trials, in a series of 6 trials. Here you see that I told you that a success and a failure are just conventional names. Here we are interested in misses, so it's more just convenient for us to say success in meaning of miss, so to call a miss a success, not the hit of a target. So probability of A can be found with the Bernoulli formula. It is equal to 6 choose 2 times 0.2 to the power of 2 times 1 minus 0.2 to the power of 6 minus 2. And P of B, probability that the 7th shot ends up with a miss. So probability of missing while shooting 7th time is the same as for all other shootings and is 0.2. So P of B is just 0.2, probability of missing in one single shooting. So how this can be simplified? So we can say that this is 6 factorial divided by 2 factorial times 4 factorial. And here we have 0.2 squared times 0.2. This is 0.2 cubed times 0.8 to the power of 4. And if we do all necessary calculations, we will see that this is approximately equal to 0.246. So probability is close to 1/4.